Hi there. Today I'm going to talk to you about something called Two-Factor Anova. Two-Factor Anova is a way of comparing how two different variables can influence a given outcome. And to make this simpler, I'm going to use the example of 3D printing. 3D printing is a newer kind of manufacturing that allows you to create 3D parts out of plastic. And when doing so, you can manipulate two different variables in order to influence the strength of that part. These are layer height and infill density. Layer height is the dimension of plastic that is being placed down on each layer as the model is being created, and infill density is the value that determines the density of the object once it is completed. In our case study, we are going to try and figure out how these factors influence a print strength. And in order to do this, we have to generate some data on the force required to break several prints, with every possible combination of variables. So in this study, we're going to use infill densities of 10, 15, and 20%, and a layer height of 0.1, 0.2, and 0.3 millimeters. Notice that I labeled KIJ equals 1. This means that for each combination of factors, for instance a layer height of 0.1 millimeters and an infill of 10%, we only had one test. If this were a scientific study, we would definitely want to have more than this. But for the sake of example, we're going to have only one. Essentially, in a two-factor ANOVA table, you compare each data point to the mean value of that factor. For instance, we compare all of the data associated with 0.2 millimeter layer height with the mean of that parameter. And the same goes with 15%, where we compare all the data associated with 15% infill to the overall average of that variable. And then we would want to compare all the data points to the overall average of an entire data set. And the result of that is three values that we can use to prove or disprove a null hypothesis. And generally, there are three null hypotheses. The first one is parameter A does not significantly affect whatever you're trying to measure. So in our case, infill does not significantly affect the strength of 3D prints. Null hypothesis 2 is always the other variable does not significantly influence whatever you're trying to test, and null hypothesis 3 is the interaction between those two do not significantly affect the strength of 3D prints. And in our case, we are probably going to disprove all of these because these variables can work both independently and codependently to improve the strength of a print. And we can go about doing that by comparing these values to a pre-known value that is based on the degree of freedom of our test. So why does this even matter? Whenever we look at data, we generally can draw a conclusion from it, but only if it's a really dramatic trend. What happens when it's not so dramatic? What happens when we introduce other factors? This gives us a definitive line between what we consider actually the effect of some variable being changed, or if it is just a product of randomness. This helps us to become more informed as engineers as we approach the real world.